starts to move you towards where we actually want to be going as far as organic chemistry goes. So what I've been hearing a lot of students going, oh, I'm going to do substitution because of X. Oh, it's substitution, it's elimination. And within that kind of statement, one of the things that's going to become problematic is you aren't evaluating the reagents you have at hand. You're only evaluating one thing and saying, oh, that means I have to do substitution. You have to look at the broader picture and see what everything is available to you before you start leveraging into just saying, oh, I'm automatically going to run these reactions. Right now, just saying you're going to run those reactions is perfectly okay because we only have a few reactions to run. Okay? But as you continue to move through the rest of this semester and into next semester, you need to shift your focus away from, oh, I just do substitution because it's a substitution section, to why do you think you need to do that? All right, and so one of the first questions that I would like you to consider when looking at something like this is, what do you see is the most reactive thing? Okay, that's where you should start your conversation. So, what do you see? Okay, so we could reference leaving group abilities. And if they were leaving groups, so this is where what we could start to do is start to mark things out. If they're leaving groups, what are they doing? But what does that mean? They're stealing the electrons, which means what we're looking at is large partial positives starting to build underneath. Does that make sense? Okay. What else do we see? And I would argue, while that's fine, that is not your primary focus. You should have seen something else as being more reactive. And I would lean away from saying strong base. Not wrong, but
NH2.
Referencing the NH2. Okay. When we go through and look at these two systems, hopefully what we zero in on is that K is a metal. And if K is a metal, that's an ionic bond, which means I'm looking at NH2 with a negative charge. That's the most reactive thing I've got in front of me. That's the thing I need to take care of as swiftly as humanly possible. Okay? And since it is negatively charged, what do I need to try and find? A positive somewhere. Okay? And now we do run into a dilemma, because if I do have that negative, it can act as both a nucleophile and as a base. Okay? And deciding between those two does become trickier. In the case of a multiple choice exam, we do have some stuff to potentially help you out within that, okay? Because you could look at your answer choices and see if the answer choices help you, okay? Which means I'm going to erase all that and take a look at our answer choices. And if we go through and evaluate the answer choices, what do you notice?
All three of them are substitution, and then one's...
Cool. 3 of them are running substitution reactions. So if we were going to run kind of just blanket guesses here, oh, that must mean the nitrogen is acting as a nucleophile. Okay, so let's leverage that and go through and run with the system that we've already had in place. Okay, so let's push the content as we see it. Okay, if that's negative, it's going to nucleophile attack, right? It'll nucleophile attack. Should this happen in 1 step or 2 steps? Why 1 step? I think Wendy mumbled it. That's strong. It's negatively charged. That's a strong nucleophile. That's going to suggest SN2, which would suggest we would get our primary reaction happening first. That could kick out. Right? We could then follow it with another reaction where it attacks the other spot, and we get our other nitrogen on there. The net result would look very similar to the answer choices that we've got available to us, except we've got a potential dilemma here. That very specifically says 3. How many did I use? 2. Why would it say 3? Okay, we can just go through and say, well, it says 3 just to mess with our heads. Okay, typically, adding information in this scenario when we talk about organic chemistry isn't trying to mess with your heads. They're trying to help guide you on a path. Because if we wanted to mess with your heads, we make a very simple edit. We just remove the 3. right? And we leave you hanging with how to navigate from there. If we're telling you there's 3, something else has to be going on here, okay? And if we push on that even further, the next step is CH3I. Okay, what is CH3I going to supply us? We've got that iodine acting as a great leaving group. We've got another electrophile, so we could talk about a nucleophile. Our nitrogen somehow coming through and reacting. Well, which nitrogen would react? Is there a difference between either of those nitrogens? The degree? How many carbons are each of those nitrogens connected to? 1. Do they have different degrees?
No.
Hmm.
They're all the same.
They're the same, which means which one attacks? If they're the same, how would you differentiate?
Just one.
Which one?
It doesn't matter because they're all the same.
It doesn't matter? If they're all the same and it doesn't matter, then both are potential answers, which would mean you'd now be in a system where you would have to bubble in 2 answers. Okay? So we can leverage the answer choices to help us be like, something's a little suspicious here. Okay? How did we get into the spot that we're in? So first and foremost, we missed the fact, or we're ignoring the fact that it says 3 times. Okay? And we only have 1 CH3. All of that seems really suspect.
Could they interact with the third NH2?
Could the CH3 interact with the third NH2? That's possible, and so that you would get 2 different products. You'd get this thing, and then the CH3 connected to that other NH2. Okay? And if that was the case, why'd you even do the first reaction? That's 2 separate reactions that have nothing to do with each other. No. So if we're going to string them together, we're stringing them together because they're doing something together. Okay? So how did we get into the boat that we got into? What started this?
Ignoring the 3.
That's actually not what started it. Say again? We went through and said that NH2 acted as a nucleophile. Maybe that was our mistake. If that's our mistake, what should it act as instead?
Strong base.
Okay? And if it's going to act as a strong base instead of a nucleophile, what does it need to do?
Gain a proton.
It would need to take a proton. What proton would it go through and take? Hydrogen is proton. The question becomes which one? I'll accept one of the 2. But that puts me in a spot because there's really only one position that has those 2 hydrogens. Okay? So we could tackle that one. Our base comes in, removes that hydrogen. What would we get? The electrons would sit on that. That would be a negative carbon. Is that a good reaction? No, negative nitrogen versus negative carbon. That doesn't work. Could I have done something else with the electrons? Instead of moving them to the atom, how about we move them to make a pi bond? But to make a pi bond, what would I need?
Positive.
A positive. Do I have a partial positive on that carbon? Yeah. So what do we need if we're going to try and make that pi bond? We would need a leaving group. What did we say the bromine was? Okay. Whether it's right or not, at this point what we're trying to do is explore our options and see where this could potentially take us. Okay. What would the result be? We get the pi bond. We still have that bromine there. Okay. We have an NH3 now chilling around, neutral. Right, that wasn't one of our answer choices, but it also said that we have 3 equivalents of this NH2. So there's still technically another NH2 with a negative charge floating around. What could it do? It could steal another hydrogen. What hydrogen do I want to try and steal?
The answers should look like another one connected to the pi bond.
So we need to steal one that sets up an option for us to stabilize those forming electrons. Where would I want to put those electrons? I would want to put them into a pi bond. So doing an elimination. But to do an elimination, what do I need? A leaving group. Do I have a leaving group? Yes, so which hydrogen do I remove? The hydrogen that is located at the beta position. Remember our beta eliminations? So our base can come in, hit that hydrogen, we move the electrons in, we kick that out. We would now have a triple bond, right? We still have the NH3 as a product, and we still have another NH2 as a negative chilling out. Okay, with that negative charge. So remember 3 equivalents. We didn't know what to do with the third equivalent in the last case. Do we have an option in this case? What did we say the NH2 acted as? A base. To remove a hydrogen, to do an elimination, because we had a leaving group. Do we have a leaving group? Nope. No more leaving group. Do we have any acidic hydrogens? Yeah? Where's the acidic hydrogen?
It's the one connected to the alkyne.
That's acidic?
It's because of the
Hold your tongue. Let me at least catch up with you. We'd form a negative charge on a carbon. Negative charge carbon versus nitrogen. Isn't the nitrogen more stable? And if the nitrogen's more stable, shouldn't I go backwards? We would say yes. And what this falls into is the trap that I told you that you need to memorize. We look at the pKa for NH3. It comes in at about a 35. We look at the pKa for the alkyne. It comes in about 25. Which way does the equilibrium favor?
NH3.
Favors actually forming the negative carbon. This is one of those things that you should have memorized. Okay? Why does it favor that negative carbon? When you're making the comparison between negative carbon and negative nitrogen, saying nitrogen's more electronegative, you're assuming the same hybridization. The carbon is sp hybridized. That hybridization increases its electronegativity. How much? Enough that we see a flip in the stability between those two things. That is a really bizarre experimental observation. That is something that you would have to memorize. That's not something you would just be able to divine from looking at this system. You have to know that. Okay? And we'll come back to when you have to know that in a second. Okay? How many equivalents of NH2 did we use? We used 3. We did 2 equivalents to do the elimination, and then we did 1 more equivalent to do an acid-base reaction. We've actually matched 1 for 1 the given information. I now have a negative carbon, though. Is a negative carbon stable? What would it need to find? Something positive chilling around somewhere. That positive thing would be an electrophile, for the record, but that's okay. So we could look at step 2, and what does step 2 supply? A positive carbon. So our negative could come in, attack, eject the iodide, and we would end up with our final product where we had a CH3 that was then connected to a triple bond that was then connected to 2 carbons. Does this account for all of the pieces? It does. Okay. And if we open up our answer choices, which I'm not going to do quite yet because I actually want the drawing here, okay, we would see that that matches perfectly to one of our answer choices. Okay. And what this one is going to hinge on is this really important chemistry of what's going on with the NH2. Okay. Running this reaction to form the triple bond is not an easy reaction to run. We need a really, really strong base to force this reaction to happen. Hydroxide's not going to cut it. Okay? That deals with pKa's, it deals with stabilities of the negatives and the carbons and all of that. Hydroxide just doesn't do it. Okay? We could use sodium hydride. Hydride is a negative hydrogen, absolutely is going to drive this reaction. But sodium hydride is now inherently dangerous, and so when we're choosing our reactions to go through and synthesize a triple bond, we typically pick the weakest base or the weakest reagent that is strong enough to do what we want. Okay? Said another way, I want to put a nail into a board. Can I use a wrecking ball? Yeah. I just hold the nail real carefully on the board, and I have my friend swing a wrecking ball at my hand to drive the nail into the board. It'll absolutely do it. Probably also destroy me and my hand, but at least I put the nail into the board. Hooray. Okay? That's sodium hydride. Okay? So I could use a really strong, incredibly active thing that would actually do it, but that's a bit overzealous. And that potentially introduces a whole bunch of secondary considerations that I don't want to worry about. So I want something that's weaker than a wrecking ball, but then still is able to drive the nail into the board. Okay? So I could switch to, I don't know, a hammer. Okay? That's the case we're encountering here. So this is one of the first cases that we're going to potentially see. This semester, I think it's our only case that we really have to worry about. That there's a line in our chemistry between where it works and where it doesn't work as far as our chemical reactivity goes. That line is really hard to define under most circumstances, which means you use your rules, charge, size, electron resonance, all of that, to deal with everything outside of the line that cuts off your reactivity, and then you memorize the line. That's the important point to nail down. So when we're talking about triple bonds, this is the reagent. Okay? Amide is our active reagent to make a triple bond. To make that triple bond, we need 2 leaving groups. We've got 2 leaving groups. We've got a strong base we can initiate. Why 3 equivalents? If we only use 2 equivalents, the instant we form the alkyne, that hydrogen, that terminal hydrogen, is more acidic than any of our other hydrogens, which means our base just goes through and starts removing that. We reduce our yield. So the only way we can maximize the yield is by using 3 equivalents, right? So that we can ensure that we've maximized that full reaction, right? Which starts to bring in the concepts of equivalence and how much you need to force a reaction to occur. Again, rare occurrences when they show up, but it does show up, and it's something that you have to pay attention to. Okay? Sort of. Why only sort of? This was one question. If you get this one question wrong, is that the end of your exam? No, for everybody shaking your head, yes. It's not the end of your exam. Right? So you have to decide where's your line on what you need to memorize versus be able to apply. And if you understand the application, the vast majority of the test can be applied, and then you'll miss some of those, crap, I didn't memorize it questions. But the way I've designed tests is to ensure that if you've got the process nailed down, you're fine on the exams, and those few memorization things, if you miss them, you miss them. It's not going to hurt your grade, despite what you think. Kind of, sort of? Okay. Note, where is this question provided?
Very last.
True, the very last. Where else is it? Multiple choice. It's put in a place because it is a challenging concept to deal with. It's not placed into the show you work because that's going to be really hard for you to go through and navigate in an open system. So it's intentionally put into a multiple choice so that you can leverage some of the multiple choice answers to help you reason your way through it. That requires test-taking strategy, but ultimately that's the most part of OChem, is how do you reason through what you're given. And for people to say, well, it doesn't happen in the real world, that's utter bullshit. It does happen in the world. Everybody reasons through limited choices. Okay? Someone doesn't show up to class. Was that because an alien abducted them? That wasn't a reasonable fucking choice. Okay? I can eliminate that from my discussion. Maybe they were sick. Okay? Maybe they got in an accident. Either way, what should I do as a faculty member? Try to reach out and be like, hey, are you okay? Okay? Are you still in the class? Those are reasonable choices, and you're choosing from the multiple choice options to try and manipulate that system. Make sense? Okay. Questions about it? Okay. What next? Okay. Whoops. So if we go through and look at B, I apologize because the font's really small. Okay, but we'll fix that a little bit. What it's noting is that we have two pathways. We can call this a nucleophile, and we can call this a base, that we get two potential options for the reagent, NaO for Naomi. So why do I need to be concerned about it acting as a nucleophile or a base? What changes about the chemistry if it acts as a nucleophile or a base?
What it does with electrons is produce protons and then
So base, we're just going to remove a hydrogen. True. Where have we seen bases in our reactions so far? We could talk about acids and bases. That's fair. Whoops. The other option that we could use is leverage our most recent content. And if we're seeing a base, we're typically looking at what type of reaction? We're running an elimination. And if we were looking at it act as a nucleophile, we're running a substitution. Right? Why could we see both of these as potential options? Because if we looked at a substitution, that could boil down into SN1 or SN2. We look at elimination, that could boil down into E1 or E2. How would I differentiate by looking at the materials to decide which of those mechanisms I should do? Okay, I could look for the solvent. Do I see a solvent?
No.
Nope. Okay. So, and I love the reference of the solvent, because ultimately what you're going back to is the four things that you're responsible for being able to evaluate when we're talking about substitution versus elimination. Solvent was one of them. We're not given solvent information, so that's irrelevant to us. So, next.
the reactants with the NaO.
Okay, so we can talk about our NaOMe. What does that thing mean? First and foremost, I see Na. What is Na? It's a metal, which means that's an ionic bond, and I'm looking at OMe with a negative charge. Okay, so that's useful as far as chemistry. That doesn't change anything about it being a substitution or elimination. What does it change? There are three components to our substitution elimination reactions. Say again? Leaving group. Leaving group is fantastic. Again, not to the OMe. The leaving group. Which of our reactions requires a leaving group? All of them. Damn it. Right? Which then sets us up in another category. We could look to the substrate. What substrate do we have? So the substrate is now looking at where our leaving group was connected. There's our leaving group. It's connected at the carbon that is secondary. And since secondary, all of them work under secondary. Shit, this is becoming really problematic. Right? What's the last thing I could evaluate? The strength of the base or nucleophile. And if it's strong, it would favor the two type reactions, so SN2 or E2. And if it's weak, it would favor the SN1 or E1. Right? Cool. Which one do I have?
Evo.
Strong and weak?
It could be both strong.
It is strong because it's negatively charged. So we're now looking at SN2 or E2. Well, I have nothing else to evaluate. Which mechanism is it going to run by? I'd have to be able to differentiate between nucleophiles and bases. How do I differentiate between nucleophiles and bases? Size. Ultimately, the steric hindrance effect. Right? And so when we go through and look at this, bases tend to be very, very, very bulky, right? Because we just want them to react with the hydrogens. Nucleophiles tend to be very, very, very small, so they can avoid the hydrogens to get in to react with our electrophile. Right? That said, can a small thing still react on the surface? Yes. Which means small things can be both nucleophiles and bases. Big things, generally speaking, can only be bases. Why does this become a problem? Is this big or small? Yes. It is both big and it is both small. Reminds me of a stupid little book that I read by kids. Right? I am not big. You are small. Right? So, if it's big and small, we can't differentiate whether it's acting as a nucleophile or a base, which means we need to do both. Right? So what you're trying to prove is, do you understand what the products would look like under each of those circumstances? Right? Because maybe we could add some more information later on in the question to help guide you to which product it was. So you have to be able to predict. So if it's going to act as a nucleophile, what's our OME going to do? It's going to go ahead and attack our substrate. Okay, and as it attacks, it's going to eject the leaving group. When? Why all at the same time? Because it was a strong nucleophile, we're suggesting 2 type, which means it must all happen simultaneously. Did we need to show the mechanism? I honestly don't remember, and I deleted the question. I don't think we did. It just said draw the product. Ta-da, there's the product of it acting as a nucleophile. What's the product if it acts as a base? Well, it needs to remove a hydrogen. Where does it remove the hydrogen from? The beta position. So if I have the context of what my beta position is, it can remove the hydrogen, form the pi bond, eject the leaving group, and I would get that as my product. All we're trying to get you to do is to acknowledge that a single species can do 2 different chemistries. Okay? Why? Yeah, we can't tell which one it does, but we could add more information into this question. We could add more information into this question saying, draw the 2 possible products that come out of this, right? And then I want you to identify the actual product because we looked at the IR, and the IR said we had a peak. Yeah, there we go. There's the excitement. Has a peak at 1650. What's our product? We know we've done the elimination because a peak at 1650 represents the carbon-carbon double bond. So we could then go through and say this was the answer. Right? So part of what we're trying to get you to think about is, what are all the things that could happen? How do we whittle down and remove some of those other things and get us into a system that allows us to understand what's going on within it? Kind of make sense? Did you need to evaluate the IR peak to answer this question? No. All we needed, do you know what it does? What happens to the reaction when it acts as a nucleophile? Do you know what happens when it acts as a base? That is it. Trying to get you to recognize those differences. Make sense? You good with that, Jackie? This is a question that's trying to get you to think about your chemistries as you go through and do it. So if we walk through this, we need the chemical, the reagent that allows this reaction to happen. So what was the reaction that happened? Okay. E2 is the mechanism. So what was the reaction? The reaction was an elimination. Right? What do we need to do an elimination? Some of that's going to depend on the mechanism. Right? So you're suggesting you want to use a strong base, and if you're saying strong as a strong base, you're saying strong, and that's why you wanted E2. Make sense? So it's not that it's E2, it's that I'm doing an elimination, and I think to do an elimination, I need a strong base, and because I have a strong base, I now know that it must be an E2. Yeah? So cool, I love that logic. So we go through, we look at it, we say, do we see a base? Yeah? Which answer choices are bases? A and D are both bases. Right? So now we have a dilemma, which is technically a dilemma on a dilemma, but we're not going to worry about that yet. Right? What is the difference between those bases? This might help if we drew it out. We're looking at that first one, or we're looking at the second one. What's the difference between those? Size. And size would allow us to differentiate between a strong base and a strong nucleophile. What did you want for this reaction? A strong base. Right? We don't want a nucleophile to run the elimination, which means our answer choice should be D. That is a lovely answer. I love how you've worked through that. That's phenomenal, and of course it's wrong. Okay? So of course it's wrong. Why is it wrong? Part of this thought process when picking out reagents is, yes, this is why I think this is it. That's awesome. Fantastic. You now need to add another layer and step behind this. That layer and step is, does it do what I want it to do? Okay? If that's my strong base, cool, let's redraw my starting material. That strong base needs to do what? Remove a hydrogen. What hydrogen should it remove?
It's going to remove the OH.
Okay? I don't accept beta hydrogen. I don't accept OH hydrogen. What hydrogen do I want to remove with a base? The most acidic hydrogen. That becomes the most important statement behind that. Right? And if you're like, but the OH is the most acidic, I fully understand that in this question. And if your focus is, I need to remove the OH hydrogen as opposed to the most acidic hydrogen, that can shift you into different pathways later on. So you need to address what the core chemistry is. The core chemistry is I need the most acidic hydrogen. If we now evaluate the hydrogens, we have a hydrogen on the OH, we have a hydrogen at the beta position. Which one's more acidic? The hydrogen on the alcohol, which means the very first thing that we're going to get would be this system with the negative charge. You'll be like, well, can't I still have my base? It's a strong base, right? Negative charge. Why can't it now come in and remove that hydrogen? Because if it did, we would need to form our pi bond, and we would then need to kick out what? O-2 would be my leaving group. Is that a good leaving group? No. That's one of the worst possible leaving groups we could ever get. Okay? We're looking at a double charge. What does that mean? That reagent isn't going to work. Okay? So that's going to eliminate all base options, which then sets us up with the, well, why the hell would I add an acid?
To make the OH better heat free.
If we go back to our reaction, let's just ignore the fact about bases or anything else and just say, what do I want to have happen here? I want to do the elimination so that I can put those electrons in, and I can kick that out. That's what I want to have happen. But in so doing, what do I have as a leaving group? OH minus. OH minus is not a stable leaving group. Right? And when we talked about the different components for our substitution elimination reactions, the leaving group is one of the last ones we look at because it always needs to be good. Is hydroxide good? Well, what makes good? Are you willing to shower in it? It's a decent starting point. Okay? Are you willing to shower in hydroxide? Your answer should comfortably be no. That's what all of your past experience through Gen Chem should have taught you. Okay? You're like, but I don't want to shower in bromide either. You're probably showering in bromide and chloride every time you finish an exam. Because it's coming from your eyes. Okay? So those ions are incredibly stable. Hydroxide, not so much. And if hydroxide's not a good leaving group, the reaction doesn't happen, so we must do something to make it better. I don't want it to be negative, which means I need to attach something to one of those lone pair of electrons. What could I attach to those lone pair electrons? How about a hydrogen from one of my acids? If I set that up, what happens? I now get a great leaving group. This is going to bring in another issue. You said you wanted to do E2, but E2 only works if you got a strong base. I don't have a strong base, which means I've got no easy way of breaking that carbon-hydrogen bond. So what's going to happen instead?
A strong conjugate base.
The leaving group will leave on its own. Once it has left, is there now an incentive to remove a hydrogen? Yes. Now that hydrogen acidity goes up enough that a weak base can come in and remove that hydrogen to complete the elimination. Okay? Make sense? So, and people referencing it as a trick question, I get where you're coming from. I totally understand it. It's only a trick question because how you've hyper-focused on just one particular reagent. You've only said alkyl halides, alkyl halides, alkyl halides. Remember, we're organized based off of what are the basic components that we need or the core components that we need to run a chemical reaction. Okay? Your practice has pushed you through alkyl halides, but if you go back and look at your practice within your smart work, you do have some alcohols showing up. Why? Because they're trying to point out that you can't just throw bases at elimination reactions. You have to be aware of your leaving group abilities. Okay? Is there yet another layer that we need to worry about? Yeah? Why? Because if we go through and look at our answer choices that we eliminated our bases, we have two acids to choose from. Which acid is going to give me the H+? Well, it's the strong acid. Okay? If your Gen Chem instructors did what I would have hoped they would have done, they would have told you to memorize the strong acids so that when you encounter a question like this, you can be like, H2SO4 and HBr are strong acids. So knowing that it's a strong acid is utterly useless. So what's the difference between those two reagents? Size, you can kind of go with that.
Compare the conjugate bases together and see which one.
When do you see carbocations?
In E1 and SN1.
In E1 and SN1. That becomes an important statement. I've got a carbocation here. I want to do an elimination, which means what do I not want present? What letter is different other than the S and the E in E1 and SN1? The letter N? The letter N in SN1 referred to nucleophile. I don't want a nucleophile. If there's a nucleophile, I'm going to get substitution competing with this. So what I've got to do is look at the conjugate bases of those two things, SO4 minus 2 and Br minus, and say, Do they have different nucleophilic characteristics? Yes. Yes, they do. SO4 minus 2 is not a nucleophile. Why? Resonance. The resonance stabilization within that structure prevents the SO4 minus 2 from doing anything useful as a nucleophile. Bromide, on the other hand, is great as a nucleophile, which causes all sorts of problems with this reaction, because if I ran with HBr, bromide is now floating around. The bromide could easily attack that carbocation, giving me the substitution product, not the elimination. Since I wanted the elimination exclusively, the HBr is a bad reagent, and I actually need sulfuric acid. A version of this question has shown up on probably 4 of the last ACS tests I've ever seen. Different variations, same formula system. Okay? Do we recognize the value of the leaving group? Do we also recognize the value of the remnants of our individual reagents? So it's something you need to see and you need to be thinking about when you navigate these. Make sense? This is your question? Did I answer it? Just depressingly so, but yeah.
So a good base in this example would be resonance in this case. So like a
What?
Like in the book, he was talking about bases. What like bases that can resonate are stronger. Is that
No, it
or
didn't.
they're weaker?
They're weaker.
Okay. So we would want weaker bases for the limit of E1.
What kind of base do we want for E1? So let's reframe the question. Okay? And something to remember, and I fully understand why you've memorized it, but we need to address that a little bit. Where did the 1 come from? When we say E1, where did it come from? Sorry. The rate. So if we look at a rate law for an E1, it's the rate equals our rate constant times our substrate, right? Does it say anything about the base?
No.
No. So when we're going through and saying we need to have a weak base to do an E1, it's actually not true. What we're trying to say is
it's just all of the substrate.
it's all about the substrate. It's not that I need a weak base, it's that I don't want a strong base, because the strong base is going to push me down the E2 path. So I just need a base, full stop. Okay? And even then, the strength of it is ultimately 100% irrelevant, because it doesn't factor into my rate law. Okay? We're adding the word weak to it just because we added strong to the E2. Does that make sense?
Yeah. It's,
Next question. Should you memorize the pKa's for all the things? This, again, comes to your strategy for how you want to navigate it. Does knowing the pKa's help? Yes. Do you need to? No. Which is not a very confident no, but no. Okay, but if you know them, it's helpful. Okay? Did you need to have them memorized to answer this question? No, why not? I gave them to you. Okay? So in cases where I want you to be thinking about the pKa's and using them and leveraging that content, I'm going to be a whole lot more explicit and give them to you. Okay? Because the expectation that you've got them memorized, I think, is a bad expectation. Okay? What I would prefer you have memorized is charge size, electronegativity, and the ability to go through and process those. Okay? So, ta-da, what are we looking at? Okay. So we want to be able to predict what happened based off of knowing some pKa's, and we're given a bunch of information. Okay? This information you are supposed to be able to go through and process. Okay? Okay, so water would be what structure? Cool. So what we could start to do is draw in some structures. Water, we have H2O. T-butanol. T-butanol is technically a common name, so that's my bad. That would be something that hopefully as soon as I opened up the exam and started to review through, I'd be like, ah, crap, I got to provide that structure because that's not one I would expect you to know. 3-methylbutine. Is that one I expect you to know? Yeah, that is one I would expect you to know. So you could go through and draw it. 1, 2, that's 3. There's 4. There's the ine, and then 1, 2, 3 methyl. And then what someone just noticed is, hey, isn't that the same thing as this? Ooh, yes. Why, yes, it is. Okay, that might come in handy. And then diisopropylamine. We're looking at diisopropyl. The amine is a nitrogen. Our isopropyl, we've got the little fish tails, okay, and then with a hydrogen on it in our lone pair. I didn't mean to change colors on that. Okay, so now we have all that information. So next part, I want you to go through and give me the definitions. Why do I want you to give me the definitions? So it's a little bit borderline here. To sort of answer the question, I want you to be able to give me all those definitions and then apply those definitions back up to what's happening in this chemical reaction. So I do want some of that application. Why am I asking you to apply put down all the definitions? If you know what an acid is, that narrows your chemical reactions. If you know what a base is, that narrows your chemical reactions. It helps you to funnel in that information. In my experience, before I asked this question on an exam, how many people lost sight of what the definition was for each of these individual reagents? Yeah, a lot. So it got to the point where even talking with people, they couldn't define what a nucleophile was. So I said, well, this is stupid. That's probably the most important thing for students to learn coming out of the class is the definition of these terms, because that's how we navigate the reactions. So I'm going to put it on the test and ensure. Okay? Give you a little bit of heads up. This is your last test potentially with me. For those of you moving on, you might see this question again where I ask you to provide those definitions. Okay? Little tidbit. If you see it on the first exam and it's semester 2, get it frickin' right. Because when you see it on exam 2 and exam 3, it's going to change. It's no longer going to be just provide the definition. It'll be if you get the definition wrong, I'm taking points away. Okay? Like literally, you just put your name on your test, I will subtract points and you will have a negative exam score. Okay? Because knowing those definitions is of critical importance to how we communicate organic chemistry. You need to have them understood. Okay? Or you need to at least have the definitions so that you can start the conversation about understanding them. Okay? It is rare for me to do that, but A section made me do that. Okay? So, we could go through and provide all those definitions. Do you want to do that now, or are you guys going to be like, I'm rock star and we don't need it? Give it to you. A Bronsted-Lowry acid is proton donor. A Bronsted-Lowry base is proton acceptor. A nucleophile is an electron donor, and an electrophile is electron acceptor. They're very easy to get confused, but you need to have those definitions with you. I would argue if this question shows up, that would be a good piece of paper to tear out of your exam and hold in front of you as you navigate everything else, because it can help you ensure that you're keeping track of those definitions. So cool. Now that we have all those definitions, how do we apply them up to the chemical reaction? Well, what changed? How do you know it was an acid-base reaction? That is a K, yes.
Okay. So we saw a hydrogen on the implied hydrogen on the left.
An implied hydrogen, yeah.
Moved.
Had to be removed so that we could get the electrons to make the negative charge. Yes. Which means this species acted as an acid, which means what does it need to react with? A base. Okay, so now we can erase all that information so I get a little bit more white space that I can manipulate. Okay, we want to find out what reagent to add in that box. Okay, so let's start with the first one. Let's add H2O. Does that make any sense to add? Why not? How would you predict H2O to react?
It would be a hydrogen at the base.
Okay, it would become a hydronium. Anybody know the pKa of hydronium?
1.4
Close.
negative.
There you go. Negative 1.4, meaning that's not going to act as a base. Okay? So what is the base species of our water? Because what we're looking at when we talk about this is our conjugate base. We need to react this with a base to form the conjugate acid. What do you think water is going to be? Does it best match the base or the conjugate acid? Probably matches the, where did I go? Oh, conjugate acid. Which means what was the base? And we get extra specific. It's not just OH minus, it must be KOH minus. Why? Because we see the K over there. Okay. Would this reagent cause the reaction to happen?
No.
Why not?
Because the pKa of the water is 15.7, and we just point back to the reactants and equilibrium.
The equilibrium would heavily favor our reactants. Okay? And you're like, but I don't like pKas. Okay, don't freaking like pKas. What could you look at? Look at your conjugate base, compare it to your base. You're looking at a negative carbon versus a negative oxygen. Which one's more stable? Negative oxygen, it needs to go that way. Make sense? So what does that mean? OH minus is not the answer. So what else do we have?
Diisopropyl and amine.
Cool, but I like to go in order. So let's take a look at T-butanol. What do we think T-butanol is going to be? The base or the acid? It's probably going to be the acid. Which means when we go over and look at the base, why are you shaking your head? Because didn't we just do that and that means it goes back this way? Yeah, the chemistry was almost identical to the hydroxide, so that's not relevant. So we could look at the butane, but that one was already given and used, so we could go through and look at the diisopropylamine. What do we think that structure is, the base or the acid? This 36 was the pKa, and the A stands for acid, which means the diisopropylamine is our acid. Whoops. So we can go back and look at the base form, and if we look at the base form, okay, does this reaction work? Well, pKa's 27 to 36. Which way does the reaction favor? Favors to the right because we have a larger pKa. pKa is the weaker acid. And ta-da! What base do we need to use? The diisopropylamide with potassium on it if we really wanted to get specific. Okay. If we tried to use the charge, size, electronegativity, all that fun stuff, we're looking at a negative carbon versus a negative nitrogen. And when we make that comparison, which one's more stable? Negative nitrogen, which runs counter. Why? Because this is the exception that I told you have to be aware of. right? And you can either go through it and memorize that you need a negative nitrogen to remove that hydrogen, or you look at the pKa's. Those were the two options. So I set you up in a spot where if you didn't have the pKa's memorized, you could still manipulate and use them, and it was now just a question of identifying what the base form was for your individual structures. Kind of, sort of? So the explaining the choice of your reagent is walking through looking at those pKa's. Arguably, you should be looking at all three of those reactions that we drew up and erased. Okay? But you can get away with not drawing all three if you recognize what you're trying to get through. So you could use words to explain it instead of all the drawings. Kind of, sort of? Does that make sense, Jackie? And since this was one that I said to memorize, you could have just immediately gone through and dropped in the middle that I need NH2 negative. Like, but dang, I don't have an NH2 negative. Yeah, you do. The H's weren't doing anything. It's the negative nitrogen that was doing anything. All of your chemistry is right there. That's it. Kind of, sort of? So this is a leveling effect question, or a quote-unquote easy application of the leveling effect solution. Which of the following transfers is most likely to occur in an acidic solution? Right? The operative word being acidic. What do you expect to see in acidic solutions? Define an acid. Donating a bunch of hydrogens. What kind of hydrogens? H minus? Okay. So when we're looking at an acidic solution, H plus, the most common thing we should be seeing would be positive charges. Right? Because we have lots of hydrogens. So if there's anything with electrons, the hydrogens are going to jump on it. Ta-da! We've got a positive. Okay, what should we not see? If you're supposed to see positives, what should you not see? So, evaluate. Okay. This first one, neutral, neutral. We'll keep it as a caveat. Neutral, neutral. Ooh, positive. That seems reasonable. Ooh, positive. That seems reasonable. Right? Which ultimately said, well, crap, every single answer was reasonable. Okay, so let's leverage that a little bit more. Andrew, you're already saying no. Barely even started. What are you saying no to? What's that?
pKa solution?
You don't even need to worry about pKa's.
Wait,
It's
is
literally
this
just
like-
positive and negatives.
Is this like the reactants or the products of the
If we're seeing curved arrows, is this reactants or products?
reactants? So
This
you-
is all reactants.
Wait, so you want negative charges? So the H's.
We do not want to see negative charges, period. In any acid-base reaction or any acidic solution, I do not want to see negative charges appear anywhere. If I have a negative charge appearing, it's a problem because the H plus would have reacted with the electrons before I made the negative. So negatives are by definition strong bases. If you're in an acidic solution, you cannot have a strong base because it's acidic. Like, that's the point. If the reactants aren't helping you, maybe you should actually consider what happens when these reactions run. If we take a look at structure or reaction A, what happens? I would get H3O plus, that's okay, but I've also formed a negative oxygen. Is that a good mechanistic step to run? No, that's showing me a strong base in an acidic environment. That is actually bad. We go through and look at B. What happened in B? Go, well, I'm forming another positive oxygen. That's a good option. What happened to the other piece?
Yes.
It also became negatively charged. That is also a bad answer. What happens when we look at C?
The positive goes away and goes to hydrogen.
So we're hearing some different answers out here. You need to take a deep breath and look at this one a little bit more carefully, because what I'm hearing is people are saying, oh, what this means is I have this where that's neutral and I get the H3O plus, which all looks kosher and dandy. Deep breath and take a closer look at what that mechanism is asking you to do.
Combine the two. So it's
What's this mechanism asking you to do?
combine the water and the.
Literally don't even know. Like, what? Right? This is someone using a curved arrow to show the motion of an atom, which 100% invalid. This isn't even on the radar because that's an invalid mechanistic step. That doesn't even make physical sense. Right? We could try and play around with that and say, well, maybe what we're saying is the hydrogen takes the electrons away from the nitrogen. That should already be screaming problems at you. Okay, which means the hydrogen or the nitrogen is now missing electrons there. Okay, and then the hydrogen took its electrons to form a bond with the oxygen. The lone pairs didn't do anything, and what do I now have on that oxygen? I have an exceeded octet on the oxygen. That whole arrow thing was trash. Okay, that doesn't match anything associated with how we would navigate our arrows. So don't fall into traps by assuming something means something. No, the arrow means exactly what it shows. Okay, so that one didn't make any sense, which then hopefully means the last one's got to be our winner. But if we go through and look at this, the lone pairs on that nitrogen, form a bond with the hydrogen. The oxygen regains its electrons. The oxygen comes out neutral. What happens to the nitrogen? Comes out positive. If I see positives throughout that entire mechanism, so I never see the existence of a strong base, that's now a legit mechanism within an acidic environment. Right? And because you are all thinking long distance, you're also trying to think and reason that you won't see this exact same question again. So what would you see instead?
Base.
Okay? What would it look like if I was in basic solution? So flip the question on its head and try and reason through that. You do have to be a little careful. You can't look at the answer choices that are provided. Okay? You could go through and say which of these answer choices might work in a basic environment, but what you're probably going to encounter is that 2 of them will work because 2 were distractors in the acidic environment. Does that make sense? So when you manipulate and retweak the question, realize you're changing your focal point on how you think through it. You can't just use the same answer choices.
So basic solution would be neutral.
So in basic solutions, what do we expect to see?
Negatives.
We would expect to see negatives.
Okay.
So you should find a bunch of negatives somewhere through your mechanism. Right? And or what should you not see?
Positives.
Should not see positives. Okay? Because again, it goes back to the reactivity of those individual systems. Make sense? Whose question was that? Did we answer that? We good? Another question? After this exam, believe it or not, I want you to get started pretty much right away into the next section of our class. The next section of our class, content-wise, has a whole lot going on with it, and it is a pain to deal with. I would argue it is the least organized unit of all units across all of organic chemistry. Okay? It's a bit painful to go through and deal with. I've gone through and attempt to make simplifications within it, but it's still going to be a challenging subject to go through and deal with. Okay? I 100% review it at the beginning of second semester, and we build on it in second semester. That may not be the case everywhere you go, so realize if you shift to a new campus, your expectations of knowing the content from Unit 4 may be higher depending on where you go. Just be aware of that. Pause. Back to our recording. If we go through and look at this reaction, if we're talking about an SN1 reaction, what are we talking about? Forming a carbocation. So we would form the carbocation where? where the leaving group is. What's the characteristic of our leaving group? Electronegative. So we can look at our substrate. Hopefully we can acknowledge that this is our substrate. Where's our electronegative element? The oxygen. Which means if we're talking about leaving group, we're talking about how that oxygen leaves the structure and leaves behind the rest of the substrate. Where's the rest of the substrate? Okay. So I heard a word that I'm going to work with. We heard both sides, so we have both sides as potential options. This becomes important, particularly if we go through and we say it's hydrobromic acid concentrated, which means there is tons of HBr around. Why does that become a big deal? That gives me lots of bromide as a nucleophile, and it gives me lots of hydrogen as an acid. Why do I need the acid? Because I want a good time. That wasn't recorded.
Put a hydrogen on the oxygen.
Why do I need to put a hydrogen on the oxygen? Turn it into a good leaving group, because it's not a good leaving group yet. So if we were going to go through and do this, we could go through, put our hydrogen on, turn that into a great leaving group, and then we could talk about how that structure left. Where do you want to leave? Leave from the left or leave from the right? I don't even really know what that means, but we'll just work with it. Leave from the left. So we'll go this way. So we go that way, we form the carbocation, we've got the oxygen with the hydrogen. We'll come back to that carbocation in a little bit. Okay, what does the oxygen then produce? Lone pair of electrons. And if I'm in the presence of a strong acid, what can happen? Particularly lots of strong acid. I can protonate again. And if I protonate again, what have I formed? A great leaving group, which means it could leave again. And that would give me yet another carbocation with my positive charge. Okay? Which then means I'm looking at my answer choices, and I would have water, and then I would also go through and I would attach the bromides to both of my carbocations. And if we look at our answer choices, that would be answer choice wrong. Why is it answer choice wrong?
From what I remember, igno.
Okay. I intentionally tried to talk through that a little bit fast because I didn't want you catching me and stopping me. Okay. I cannot form a carbocation on a ring. That's not allowed to happen. Okay. Do you have evidence of that? Everybody said, yeah, of course we have evidence of that, Mike, because we tested that in lab, and in lab it didn't react. That's why we do it in lab. When we're talking about leaving groups attached to rings, they do not react. You cannot do a substitution on a ring. That very first arrow that we showed is invalid. It does not happen. Okay? So if we backtrack through this, kind of upset that I got to erase it all. Probably didn't have to erase it all, but we did it anyway. We would get our tertiary carbocation. That tertiary carbocation can continue on to go through and give us the bromide substitution. The other structure, it doesn't matter if I protonate that oxygen, that's still not going to form a stable carbocation. So what happens? It eventually ditches the hydrogen back to solution, and all we end up with would be this as a product and this one. And that's what we get. So we have to be aware that to run this reaction, number one, there are two potential sites to act as substrates. That becomes an important distinction. Okay? Because oxygen has two bonds that can potentially go both ways. Okay? We then have to evaluate the validity of having the leaving group leave from that site. And in this particular case, if it left from the ring, it's forming a very unstable carbocation, which is unlikely to go through and form, which means I don't get to do a second substitution. I really only get one. Okay? Why is it important to acknowledge that we have two active sites? Let's erase all our answer choices. What if I switch the question up?
Doing secondary versus tertiary.
So we could worry about secondary versus tertiary, right? So let's go ahead and throw something else on there. Right? So now we'd be in a spot where both of those sides could run through the substitution reaction. Because we've changed our starting substrate to be active at both those sites, we would get both substitutions. Does that make sense? So you have to pay a little bit careful attention to recognizing where your chemistry is. In this case, it's on both sides, but one of those sides, or in this case, as shown, both sides are active substrates, and it's just going to depend which side reacts. Right? Is one preferenced over the other? Yeah, so one will go first, but if I'm in concentrated acid, everything's going to run.
So we're both sides were tertiary, but
What if both sides were tertiary? Both sides are going to react. So in this case, they aren't asking which one happens first. Okay, so if they were both tertiary, then maybe we'd have this argument of, okay, well, what's going on? But if we wanted that conversation, what we do is a tertiary and a secondary, and we could say which one forms first. Again, super rare. All we're really doing is trying to push and get you to realize that there's two active sites to consider. Make sense? Okay, I'm going to stop the recording.